Right, let's get started. We're still talking about the ACI 318-14. We are doing some worked out examples. This is a session. Um, we are continuing the previous session here. We ended up doing a couple of problems. We talked about a bunch of concepts and then did a couple of problems. In the last session, we ran out of time. Now we're picking up from where we left. We'll be doing a problem on shear. How to find your shear capacity, like VU or phi times of Vn, right? We'll be doing one problem on that. We'll be doing a problem on finding the same shear capacity, but when when an axial load is present. Okay, we'll also find out. We'll also do a problem on how we can find out. Let's say you have a beam. A beam is subject to certain forces. Then how you can find out. Let's say this is a compression reinforcement, tension reinforcement, and these are the stirrups. How do you decide the spacing of those stirrups? We'll do a problem on that, and then we'll do a problem wherein there's a column subjected to an axial force, but then we're not asked to calculate the axial capacity, but then we're asked to calculate the flexural capacity of the column. Okay, so we'll see how we can look up something from an interaction diagram to see how we can calculate given a certain moment, how can you pick up an axial force, or given a certain axial force, how can you pick up your moment based on your percentage of reinforcement and all that. Okay, um, so there's a lot to cover. So let's get started with the first one here. Okay, first one, pretty straightforward exam problem. Okay, looks like, so here is how the beam section looks. Okay, so that's a beam. Width appears to be 10 inches, and the overall depth from here to here appears to be 16 inches. Okay, now there is obviously there are some number of bars, tension reinforcement. You have a stirrup like that, right? Obviously you have some amount of compression reinforcement too, so that we can hang your stirrup. So the stirrup itself is number 3 at 4-inch spacing normal to the screen. The main reinforcement AST is these are number 8 bars, 4 of them, right? And let's read the problem statement. The problem statement, RCC section is shown here. Determine the design shear strength. Design, when they say design, you take your nominal shear strength and then multiply it with the strength reduction factor, and that is the value that you use in your design, or that is the value you design your beam for. Okay, so breadth is given, depth is given, area of steel is given, area of compression steel is given, FC prime and Fy are given. Okay, so we start with calculating the effective depth. This is the overall depth, but to calculate all the shear capacity, we need something called effective depth, right? So effective depth is nothing but the overall depth minus, if I blow up this section here, let's say you have a beam, bottom of the beam like that, right? The reinforcement is somewhere here, and let's say the stirrup is running like that. So there is a spacing called clear spacing, so that is 0.75 inches from here to here, right? Edge from outer edge to the outside of that. So you reduce the clear spacing 0.75 minus diameter of one stirrup bar is 3 by 8 minus 0.5 times of your number 8 bar. Okay, half the diameter of number 8 bar, right? So that means again, if I do it like that, blow it up, I'll just add one bar, right, and one stirrup. Okay, so if that is a clear spacing, that is 0.75 total depth minus the clear spacing, then you are here minus 1 bar diameter, then you are here minus half this bar diameter, that is you are to the center. Okay, and it is the dimension to the center which we are trying to calculate. So that results in 14.375. Let me reduce that a little bit. Okay, 14.375 is your diameter of, effective depth. We know that the strength reduction factor for shear 0.75, correct? Then we were asked to calculate what? Phi times of V nominal. Okay, that means you know that phi times of V nominal is made up of V concrete plus V steel, right? And we start by calculating VC. VC is nothing but 2 times of lambda square root of FC prime into BW times of DW, or times of D. So that is nothing but 2 times of lambda 1.0 normal weight concrete FC prime given in the problem statement times of the breadth times of effective depth 0.375. End up with 17.25 kips. Okay, so that's the capacity of the concrete. Capacity of the steel is nothing but AV times of your Fy times of D by S. We talked about all this in detail in the previous session. So AV, how many legs are cutting? The 2 legs that are cutting. So your AV will be 2 times pi number 3 bar. So 3 by 8 inch square by 4. So that is 0.221 inch square. So use that AV value here 0.221 6010 cube, right, times your depth, effective depth 14.375 times your what is the spacing normal to the screen. So 3 number, number 3 bar at 4 inch spacing normal to the screen. Okay, so calculate your value. It ends up to be 47.653 kips. But remember to compare this with your upper limit, which is 8 times of fc prime square root of fc prime gamma lambda is there obviously, bw into d. Okay, so that value comes out to be the maximum. This is the upper limit, comes out to be 69.0 kips. The value that we calculated is less than that, so we are good. So that means we can calculate our phi times of vn as phi is 0.75, vc 17.25, vs 47.653, roughly 48.67 kips. Okay, so that is the design shear strength, not the nominal. Okay, so quick recap. We are given the geometry, so we calculated. We were given B and D, right? D and B. We're given the stirrups, information about the main reinforcement, the spacing of the stirrup 4 inches normal to the screen. Given all this, we were asked to calculate the design shear strength. So we started by calculating our effective depth, which is most important, and we did that by from looking at our clear spacing, number of the bar diameter from here to here, and then the half the diameter of that one. So we had to subtract all that from the overall height to find our effective depth. Shear strength reduction factor for shear, right? We cannot be spending time in exam looking up the value. We have to sometimes you have to memorize all stuff like this. Then contribution from concrete, contribution from steel, contribution for concrete, calculated value appears to be 17.2, contribution of steel to shear area times the number of sections, right? So you calculate that, appears to be 47.65, and there's an upper limit to that, so you compare it with upper limit is 69, value calculated is 47 point something, so we're good. So that's so you combine those two, multiply it with the shear strength reduction factor, that is your answer. Okay, so that is the problem on flexure. So now let's do another problem on finding the nominal shear strength, but this time is slightly different. So you're trying to calculate your nominal shear strength. Let me draw the beam. It's going to be difficult because it's a circular. So this is a circular column, looks like, right? Shear column. So this is a column, and obviously there is a spiral, ties, regular ties, right? The diameter of the tie is number 4. number 4 at what spacing? At 4-inch spacing normal to the screen, right? And then there are a bunch of longitudinal bars, right? And those bars, I'm not drawing the exact number, but there are 10 number 8 bars. The diameter of the column is given as 24, and we are asked to calculate, and this column is subjected to a certain axial load, right, pu, and we are asked to calculate the nominal shear strength. Okay, so the ask is to calculate just the v, um, and v nominal. Okay, and we are not multiplying with the strength reduction factor to calculate your v design. Okay, pretty straightforward. We see 2 lambda root fc prime bw into dw d, right? But we'll not use this because this doesn't capture the effect of your axial load. So we talked about this in the last session. We'll use something with the additional factor of 1 plus that axial load divided by 2000 times your a gross, everything, all these formulas in the code, and we talked about it in the last session. Fc prime times of Pw and D. Okay, so for a column like this, your B, which is a circular column, there is no Bw, but then the code says Bw can be taken equal to the diameter, which is 24 inches, and Dd is 0.8 times your diameter, which is 0.8 times 24, 19.2 inches. Okay, so that is how you arrive at P and D for the code. So when you do that, substitute those values. 2 times 1.0 times 1 plus 200 kips, so 200 pounds, 2000 a gross. A gross, how do you find a gross? Is pi into the diameter of the column squared by 4, 452.38 inch square. Okay, so 452.38 times fc prime, that is 600. Your breadth, it's not a rectangular column, but the code value, and your depth is 19.2 inches, right? So the whole thing, when you calculate it, comes out to 67.51 kips, and this is v nominal, and that is what is asked. Okay, so simple example, but then demonstrating the importance of capturing the effect of the axial load on your shear strength of nominal shear strength. And they're not asked, they were asking of nominal concrete shear strength, so we are talking about only VC here. Okay, let's go to the next problem. That appears to be a problem on finding the spacing of stirrups. Right, so let's see what the problem says. We have to find the spacing of the stirrup of the RCC beam shown. Let us show it then. That's your beam looks like, right? And then 3 bars here, and 3 bars here. There's one stirrup which is going all round, right? But there's another single tie which is like that. Okay, so the ties are number 3. The breadth of the beam is 9 inches. This one here is 16 inches, correct? Clear spacing is 3/4, so if you take that, reinforcement, stirrup, right? Clear spacing is 3/4 inch, right? So we start by, the shear to which this whole thing is subjected to, Vu, is factored shear is 34 kips. They're asking us to find out if you have, if let's see the beam in the other direction, asking, let's say bottom reinforcement, this fellow here, right? Top reinforcement, that fellow there, and then a bunch of stirrups, correct? you need to find out what the spacing of these stirrups is, right? So let's get started. Before we do anything, so what is being asked is VU, which is nothing but phi times of Vn, which is nothing but phi times of Vc, contribution from concrete, contribution from steel. Okay. Effective depth is the total overall depth minus your clear cover, right? Minus one diameter of number 3 bar, right? That is this bar here, and you go to half the diameter of these bars here are number 9. So have the diameter of number 9. Number 9 diameter is not 9 by 8. The diameter of number 9, you have to look it up from the table, is that value there. Okay. So that is close to 14.875 inches. That is your effective depth of the beam. Okay. We calculate VC 2 lambda root FC prime BW into DW or D, which is 2 times 1 times square root of 3600. What is your B? 9 inches. What is your effective depth? 14.875 inches. The value comes out to be 16.065 kips. That is your VC. Okay. Now you calculate VS. We don't know. We don't know the spacing, so that's what we are looking for. So we need to find out what Vs is. Okay. So Vu is nothing but phi times of Vc plus Vs, right? So Vu, kick the phi on the other side, Vu by phi minus the Vc is nothing but Vs, right? So Vu given in the problem statement here. So this is nothing but Vu is given as 34. 0.75 is the factor. Vc we just calculated is 0.265. This is Vs. That means Vs is 29.268 kips. Okay. So we found out Vs. What is Vs? Vs is 29.268 kips means times 10 cube pounds. This is nothing but area of the shear reinforcement, Fy, and how many of those. Okay. So again 29.268 10 cube, right? What is the area of shear reinforcement? We have 3 legs. Okay, so AV, we have three legs here cutting 1 2 3. Okay, 3 bars. So your AV is nothing but 3 area of number 3 bar, 3 by 8 square by 4, that is roughly 0.331. This is 0.11. Okay, so 0.331, 0.331, 60 10 cube. Diameter, effective depth, we calculated that as 14.875. Spacing is a question mark, right? So equate left hand side to right hand side and find out your spacing, that is only unknown, comes out to be 10.10 inches. Okay, and in the exam you will have an answer as 10 inches. If you choose that, you're wrong, because you need to check the maximum shear spacing. Okay, we talked about it earlier. For a non-prestressed beam, this value is the minimum of your d by 2 or 24 inches. D 14.875 by 2, 24 inches. This 7 point roughly 43 or whatever. Okay, so the minimum of 7.43 and 24 inches is your, so that means the S max is 7.43 inches. Okay, and in the exam, that means in the exam you'll have an option close to 7, and you need to pick that. So the final answer is you have a beam, you have your stirrups, right? Those stirrups, uniform spacing, obviously. Channel itself is chicken scratch, so I don't have to ask you to excuse me. So this is 7-inch is the answer. That is your stirrup spacing. Okay. Let's recap real quick what we did. We were given beam geometry, we are given the shear reinforcement details and the details of the main reinforcement, clear cover, diameter of the stirrup bar of this bar, right, and diameter of those bars. So we found out from the overall depth, we found out how effective depth can be calculated. We found out how VC can be calculated. VC is the strength of the shear strength that concrete can offer. Then we found out what the VS should be, because we have been given an overall VU, right? So we found out that the shear reinforcement has to take this much load. Okay. Now we calculate based on the area of we equated the strength to the um, um, the demand to the strength, and then found out that my spacing has to be at least 10 inches. I mean, if the spacing is 10 inches, then we are good. But then we didn't stop there. If you stop here, most people stop here, then we end up with a problem. The S max, maximum spacing per the code, is the minimum of this value and that value, and the minimum comes out to be 7.43, and that, so we have to provide a stirrup at 7 inches. Okay, that's about this problem here. Let's do the next one. It's a little more interesting problem. Okay, let's copy statement. That's the problem statement. So they're asking us to calculate the flexural strength of a cross section shown. So let's show the cross section. Appears to be a square beam, right? With reinforcement like that, and a stirrup all around. Okay, the dimension 15 inches. So this dimension is 15 inches. Okay, clear spacing from there to there, 1.5 inches clear. Then diameter of the main bars is number 7. There are 8 such bars. Diameter of the stirrup is number 3. Okay, number 3 stirrups. And interestingly, this beam is subject to a dead load, or this column is subject to a dead load and a live load. So in other words, here is a column, that's the column. Here is our longitudinal reinforcement, right? Here is our stirrup, and there is an axial load. Axial load is made up of a dead and a live component. Dead component seems to be 110, live component seems to be 85 kips. Okay, so you have dead and live. And what are we asked? We are asked to calculate the design flexural strength. Okay, not axial strength or anything. It's an interesting problem because you're given the axial load and you're being asked the um, what is the maximum moment to which you can subject this column without uh, it undergoing failure. Okay, area of reinforcement and all that is given. I think these are, let me check if this is number 8 bars or number 7 bars. This is number 7. Okay, right. So let's get started. We'll start with finding the gross area. Okay, AG, pretty straightforward, 15 inches by 15 inches, 225 inch square there. We calculate the area of steel. You have 8 number 7 bars. Inch square there. Okay, then you so given that information, we'll calculate something called what is the axial. So the moment capacity will depend upon the axial capacity. Okay, so if you subject the column to a very high axial load, um, versus a very low axial load, the moment capacity of the column will change. Okay, so that means there is an interaction between your p value that you can subject the column to and your m value that the column can handle. Okay, and these are called interaction diagrams. So we'll have to go to the code to find out where the interaction diagram for this particular column is, and then calculate some non-dimensional values, and then calculate your mn value based on the given p information. Okay, so before we do that, let's go to the I mean, we want to find out our axial capacity of the column, right? So phi times of pn, right? But for a column, we have seen this earlier. We'll take a look again. So this is nothing but 0.8, um, sorry, this is nothing but a phi is 0.65 times 0.8 times of your Pn max. So sorry, P naught. Okay, so this itself is called the Pn max. We'll take a look. Let's go to the code and find out where that value is. Axial strength, roughly somewhere there. Okay, so that is, like I said, this is axial strength of column, right? Nominal Pn shall not exceed, so that means less than or equal to Pn max, right? And Pn max is given in this table here. We are not pre-stressed, we are not composite, that we are non-pre-stressed, we don't have spiral ties, that means we are here, that means this is our Pn max. So P nominal is 0.8 times of P naught, and the P naught itself is given here. So P nominal is 0.8 times of 0.85 Fc prime A gross AST plus Fy times of AST. Okay, so now that is the nominal, but phi Pn means you multiply the whole thing by phi, the whole this entire equation, Pn equation with phi. Okay, that's how you calculate your phi Pn. Why do we calculate phi Pn? We'll have to get into something called the interaction diagram to calculate the moment capacity given the fact that the column is already subject to a certain axial load. Then that is why we are calculating our Pn value. Okay, so I'll calculate in the Pn again. So 0.65, that's a factor, and then 0.8 times P naught, 0.8 times your P naught, and P naught is again 0.85 times of Fc prime, Ag 225, AST 4.81 inch square plus 60 10 cube Fy times of AST 4.81 inch square. Okay, so you calculate that, and that is your phi Pn design axial strength of the column, 539.36 kips. Okay, you do that and you calculate your flexural strength. So now the idea is to calculate your flexural strength ultimate. So that means you calculate the nominal, you do the phi times of m nominal to find out your value there. Okay, so this is where we need to understand some more details. For example, if you go to the, so these are called interaction diagrams, right? So this is where your column is subjected to a certain axial load, and then you're trying to calculate the capacity, bending capacity about a certain axis. Okay, so based on the configuration of your column, you will have to pick up the right curve. There are a bunch of curves like this, right, in the P handbook, right? So how do you pick up the curve? You have to look at the column and find out something called the gamma value based on the h. So that is h, but from the center to the center of the reinforcement is called gamma times of h, right? So if you know h and you know the space, this gamma, this distance here, then you can find out your gamma. Let's say the gamma is 0.6, okay, and your fc prime in the problem statement is 4000, and the steel you are using is 16 to 10 cube steel, okay. If those parameters match, then here is an appropriate curve, because this curve has a gamma of 0.6, fi of 60, and fc prime of 4 ksi. Okay. Now let's talk about the curve a little bit. There are two non-dimensional terms, one on the y-axis, one on the x-axis. This non-dimensional term kn is a function of your p axial load, and this nominal non-dimensional diameter rn is a function of your m. Okay, but you don't see m, but you see p and e. So p times e is the eccentricity, is nothing but your n, pn, so that is mn. Okay, and then there are a bunch of lines. All these lines, for example, that line here is nothing but an interaction curve for a column which meets all this requirement and has a reinforcement ratio. That means rho, which is AST by B times of D. What is AST? AST is the area of steel that you have, longitudinal steel in your column. Okay. What is B? That is B. What is D? That is D. Right. So in this area, what is the percentage of this reinforcement? That is AST by BD. That is this value here. If that value is 0.002, then you were talking, sorry, 0.02, then we are talking about this curve. If it is 0.07, then we're talking about, then we have to refer to that particular curve. Okay. So let's go back, calculate the gamma value, and then see where we end up. Okay. So the gamma value is again distance between the reinforcement, right? So we need to take a little bit of caution in computing that value. Okay, so to find out the gamma value, let's draw the picture one more time of our column, right? So reinforcement like that, reinforcement like this, and reinforcement like that, right? That bar diameter is, what is the diameter of the bar? Number 7. So these bars are number 7, number 7. Then you have obviously stirrup around them, right? That stirrup is number 3. Okay, so we need to calculate the distance from here to here, because that is our gamma h. We know what our h is. H is 15 inches. Once you know 15 and you know gamma h, then you can calculate gamma. That's the idea, right? So let me blow up this section here, and then we'll talk about how this whole thing can be calculated. So you have your stirrup coming like that, going around, right? Let's give it some thickness. So let's say that is your stirrup, and it is at a not 90 degrees like that. So it is at a bending radius. It's at certain radius, right? And then, so let's say that's the center point, and that is the radius of the stirrup. Then you have your bar, number 1, number 2, number 3. Okay. So how do you find the spacing? You take the total 15 inch, right, from the edge of the concrete to this edge. That is your from here to here. That is your clear spacing, right? This example is 1.5. So what you do, you take 15 minus the clear spacing 1.5, 2 times of 1.5, because one on this side, one on that side. Now you delete the diameter of the number, you subtract the diameter of the number 3 bars. So how many 3 bars? You have 2 number 3 bars, right? And then you uh, and then you have to still come here, right? So there is, if there is a stirrup like that, and the stirrup diameter is, I mean, the stirrup is not just doing a 90-degree turn like this, right? So the stirrup is going like that. That means there is a certain, it has a certain radius, right? That means, so that radius is based on the diameter of the stirrup. If the diameter of the stirrup is number 3, sorry, if it is a number 3 bar, then the radius is 2 times the diameter of that bar there. Okay, so that means from here to here, that is the radius. From here to here, that is the radius, right? We're talking about something like this. So that means we have to we're talking about this distance here, right? So that is 2 times of your diameter of number 3 bar. Okay, so again we are trying to calculate your spacing, which is gamma h, right? Because gamma h is from here to here. The gamma h value, the 15 overall width, 2 times your clear spacing. That means we are here. Then you reduce one diameter on this side, diameter of the stirrup on the other side, and then you account for the radius, that distance there, 2 times. So if you do this, you will end up with 9.75 inches. Okay. So your gamma times of h is 15 is 9.75 inches. That means your gamma value is 9.75 by 15, roughly 0.65. Okay. But if you go back to these curves, there is a gamma of 0.6 and there is a gamma of 0.7. Yes, you can interpolate between these two, but you have to do that 2 times. So for just for the demonstration, let us assume that this gamma is 0.7 inches, or let's assume that this is 0.6 inches. Okay, so no, you assume 0.6 inches. Now we know which interaction diagram to go to, because here is an interaction diagram with our gamma as 0. With our gamma as 0.6, Fy as 60, Fc prime 4 KSI. Okay, let's calculate the Kn value and calculate the percentage of steel, so that we know which curve we need to follow, and then we come back and calculate our Rn value. Okay, from the curve. Let's go back here and calculate our Kn value. Right. Again, Kn is the parameter that is here on the vertical axis, which is rho nominal by Fc prime times of A gross. Okay, so how do you calculate what is Pn? Pn is nothing but Pu divided by phi. What is my Pu? 1.2 times of P dead plus 1.6 times of P live factored divided by phi. What is my phi? 0.65, right? So 1.2 times of 110 plus 1.6 times of your live was 85, I think. The problem divided by factor is 0.65. That is your Pu, Pu by phi, which comes out to so that is your Pu, and then you calculate your Kn as the P nominal by Fc prime times of Ag. So you divide this value here by Fc prime is 4000, Ag is 15 by 15. Okay, so this value here is nothing but 1.2 times of dead load, 1.6 times of live load divided by factor 0.65. Okay, so if you do all this, you end up with your Kn as 0.46. Okay, so we know Kn. Now we need to know to find out which curve we need to follow. You need to find out what your percentage of reinforcement is. That is nothing but AST by P times of D. What is your AST? You have 4 point, I think you calculated that as 4.81 divided by B is 15 by 15, roughly 0.021. Okay, 0.021. Now go to the curve here, put this line exactly at 0.46, because that Kn value, the Kn that we calculated is 0.46. So this is 0.4, 42, 44, 46, right? Draw this horizontal line, and the rho is 0.021, right? So let's say this is 0.02. That means we are talking about that curve. Okay. So you take curve, highlight the curve, and this is the line, horizontal line. They intersect at that point. Drop a vertical line there, and you find out that this value is 0.165. It is cutting that axis at 165. Okay. So 165 is your Pn times of E by Fc prime times of Ag times of H. Okay. In other words, you can replace this as Mn. So Mn is nothing but 0.165 into Fc prime Ag H. So that's how you calculate your Mn. Let's do that here. So we calculate our Rn. We know that from the curve Rn is 0.165, but we know that Rn is Mn by Fc prime Ag into H. Mn is what is the unknown. So Mn is nothing but 0.165 times all this. Okay, Fc prime 4000, A gross is 15 by 15, right? Times of H is another 15. You calculate that, comes out to be 185.625 kip feet. That is your Mn. Phi Mn is what has been asked. So phi is 0.65 still. It's not 0.9 or anything. Still, this is the most important thing. You'll have an answer in the exam which is 0.9 times of 18.625, but you have to use, and you'll also have an answer with 0.65 times of 185.625. So that turns out to be 120.656 phi mn is that much. So what did we do? We had a column which was subjected to a certain dead load and a certain live load. That means it is being subjected to a certain factored load, right? And the column had certain amount of longitudinal reinforcement. Obviously it had a certain area, so that means there was a certain percentage of steel, which is AST by BD, correct? And we were asked to find out what the capacity, what is the maximum moment that you can apply about a certain direction, okay? Or what is the design moment to be specific design value. Now, how did you find that value? We because axial load, we know that axial load interacts with your moment. We had to go back to a moment. We had to go back to um, the moment interaction diagram. On the y-axis was a Kn, on the x-axis was an Rn, and this diagram what was for a specific Fc prime, specific Fy, specific gamma value. The tricky part was to calculate your gamma value. The gamma value was just based on the geometry. We had bars like that, and we had to find out the center to center value, which is gamma h. We knew our h, and we had to calculate our back calculate our gamma, and it turned out to be 0.6. So for gamma is equal to 0.6, Fy for the 6010 cube steel and 4000 psi concrete. We went into the PE handbook, found out an interaction diagram, but there are a bunch of lines on it. We picked up a line, we followed a line that had a percentage of reinforcement rho as 0.201 or something like that, right? So we found out our K value, we dropped our vertical down and found out our Rn value. That value turned out to be 0.165, and then we know that Rn is Pn times of E by Fc prime into Ag times of H. So we calculated our Pn times of V, which is nothing but Mn value. Okay, we took that Mn, we calculated that Mn here and multiplied with the strength modification factor of 0.65, not 0.9. 0.9 is a wrong number, right? And then we found out that the moment capacity is so much. Okay, so that is what we did, and that is the recap for this particular problem here. Let's move on to the last problem. interesting problem here. This is about the punching shear. So let's paste the problem statement right there. Okay. Problem statement there. So we are given what? We are asked punching shear, but we have been given with given a cast in place floor system with a typical span 30 in each direction, supported on an 18-inch square column. Determine the design punching shear. So we are putting all our concepts about punching shear that we learned last time to test here. Okay. Um, Interesting thing is this column here is not at center. Oops. This column is like that. This is the slab edge of the slab, and this column is somewhere here, right? So this is the plan view. But this is in general, this is a flat plate. Whenever it is a flat plate, it is something like this. Remember, a flat plate is like that, whereas a flat slab might have a drop panel like that. So the terminology should be clear. So this can be again a drop panel or a shear cap. I'm talking about this piece. Can be either a drop panel or a shear cap. So this is a flat slab, whereas this one is a flat plate. Okay. So we are given a cast in flat plate system. 18-inch is the diameter of the column. This is a corner column, meaning that is the edge. So this is an edge of concrete. That's an edge of concrete. Whereas this side is continuous. This side is continuous. Okay. Now we need to calculate the punching shear. So imagine you take a cookie like that, right? Cookie, just a biscuit, right, which has some thickness, and let's say you hold it with your hand at that point, simulating uh, the column there. Okay, so you hold it with your thumb, you hold it with your um, index finger, and then at the bottom maybe you put your thumb like that. Okay, so that's your hand. Okay, that's your hand. This is your wristwatch. Okay, you're resting your arm on a table. Maybe you have a sleeve, right? Something like that. So you're holding it at this point, and imagine there is a lot of live load and dead load on this particular. Maybe there are other pinch points, but then there are simulating other columns. But once that happens, what if you press the cookie down? What you will see while you are holding here, what you will see is that um, your cookie will uh, break like that, right? Leaving this portion in your hand, everything else will fall down. Okay, so portion which is like that is gonna it's gonna come out, right, leaving in your hand that particular portion. Okay, that's exactly what the kind of visualization you need when you are calculating your um, punching shear, right? Because you need to find out the critical section for the punching shear first, and then you can calculate its strength. Okay, so the critical section, like I said, um, is going to be a plane which is d by 2 from the face of the support. We talked about it in our two-way slabs and all that. So some section which is at d by 2 from the face of the support. D is the depth of the column, and also d by 2 from the face of this side, which is something like this. Okay, so let me draw it like that, and this is the cookie portion that will remain in your hand. Okay, in other words, um, let me like that. Let me this part. Okay, so we need to calculate this length and that length, and that is the now you look at it in a 3D view. This side is continuous, right? So this side is continuous. That side of the concrete is continuous. This is the thickness of the concrete slab, right? Here is a column, right? This is where our column is, and and the shear, the critical parameter, sorry, critical shear plane is something like that, right? So critical shear plane is like that, and it has a certain, obviously certain depth, right? So that means the critical shear area is that area here. Okay, so that's in 3D. That is the area that is taking the. I mean, if you know the shear stress, let's say you know the shear stress on, and then you multiply that shear stress with this area that is taking your shear, then you can find out what the how much shear load this particular concrete slab can handle. Okay, before a punching failure can set up. So let's clear that crap and start um, finding out that particular value. Okay, so the information from the problem, this distance appears to be 3 feet. This distance here is given as 3 feet. Obviously it is out of proportion. This is only 18 inches. Okay, critical shear plane is at d by 2. So let's find out what our d is. Okay, the problem statement has the d is 7.5 inches. D is nothing but, if you look at this slab in this view, or here, d is the distance from the top to the reinforcement that runs in the slab there. So 7.5 inches is our d. Okay, so what is this critical distance? So that distance is, let's calculate this, and then we calculate that and add them up. Okay, so that distance here from here to here is, you have your 36 inches, 3 feet, then you have your 18 inches width of the column, then you have your d by 2, which is 7.5 inches by 2. Okay, so that means that distance is 36 inches on this side, 18 inches on the other side, plus 7.5 inches on this side. Okay, the same story repeats in this direction, because you have your from here to here is your 36 inches, right? And from here to here is your 18 inches, and from here to here is your 7 d by 2, which is 7.5 by 2. That means the critical, that means these are two, there are two such uh, um, edges. Okay, so that, if you do this value, this is called as b naught in the code. Okay, that amounts to be 115.5 inches. Okay, so now we talked about this vc in the code. This is small vc, that means your shear capacity of the concrete. um, you have to find out 4 times lambda. You have to find out something called 2 times 4 by beta, and then there are 3 numbers. There's an alpha naught times of alpha times of d by b naught, I think. Okay, and then you multiply this with your fc prime, square root of fc prime into bw into t to find out your value. But we'll have to pick up the minimum value from this. So obviously 4 times lambda, normal weight concrete, so this is roughly 4. This one, the beta, is nothing but ratio of long side of the column to short side of the column. We have a square column, so beta is 1. That means this one is 4 plus 2, roughly 6. So this does not control. Now we have to calculate this. This is 2 plus alpha naught. This is an interior column. We talked about it again in our two-way slabs and a bunch of other sessions. Interior column. So alpha for the interior column is 20. Okay, so this is nothing but 2 plus 20. Depth is 7.5 inches by b naught. We just found out b naught as 115.5 inches. So this is roughly 3.298. So this is 3.298. This is 4. This is 6. The least is 3.298. Okay, so um, your VC is minimum of all that. Minimum of what? Minimum of 4, minimum of 6, minimum of 3.298, right? And that means it is 3.298. Okay, now we take VC, and that this is the stress, and we multiply with the uh, um, sorry, we still not at VC. We have calculated that parameter, that these parameters. Now VC is that parameter, the least parameter 3.298 times of square root of FC prime into BW into D. Okay, so 3.298 times square root of FC prime, that is 600. B, but this B is the area that I was talking about. So that area in the concrete slab, that area which takes the shear, right? Here, this is where your column was, and this is the cookie that will remain in your hand when you try to break it. Okay, so that area is nothing but your B naught, which was 115.5 times the effective depth, which is the depth there, 7.5, from the top fiber to the compression fiber to the bottom of the reinforcement. So that is 171.45 kips. So that is your VC. Okay, but we want phi VC because we want the design in shear, that is your modification factor, 171.45 kips. This is nothing but 128.58 kips. Okay, so that is your design punching shear strength, right? That means you need to apply 128, something greater than 128.58 for to break the cookie here. Okay, so just to recap, we were given just to recap here, we were given the slab. We were told that this was in a discontinuous edge. We were told that this column is at the corner. That means alpha value is 20, and we had to calculate our punching shear strength, determine the design punching shear. Okay, so before we do anything, we had to calculate the critical section, where the critical section is, and that critical section length was found to be 115.5 inches. Then we had to compare these three values in the code and pick up the minimum. One is 4 lambda, one is 2 times of 4 plus beta. Beta is the ratio of long side of the column to the short side, in this case square column, so it is beta is 1. Beta is 1, that means this whole thing is 6. And the other number is a function of alpha naught, D, and P naught. Obviously, I mean, fortunately or unfortunately, that is what governed, because your D naught was that much, this is this much ratio, 1.298, right? This value is 1.298, and you add that to 2, 3.298. But 3.298 is the least when you compare 4, 6, and this number here. Okay, so you pick up the least value, and then that times root lambda, obviously times root FC prime BW into D. That's your shear strength, VC. Now we're talking about a big VC. So that is 3.29 square root of 3600. BW is nothing but B naught, because which is the width of this, and that, right? This was 115.5 by 2, 115 by 2. That means 115 times your depth is 7.5. So your VC was that much, but the design. So the answer, there will be one answer like that. Okay, but you have to multiply it with 0.75 times that to find out your design punching shear strength. Okay, so we talked about a bunch of problems here. We talked about a problem wherein we calculated, given the beam section, we were given some shear, and we were asked to calculate some reinforcement and all that. We were asked to calculate the shear capacity. We had a problem wherein the beam was not only subject to shear, but then there was a slight axial load acting on it, and we had to calculate the shear capacity. Okay, then we had a problem wherein there was where the reinforcement was given, the shear information was given, the shear was given, ultimate value I think 34 kips or something, and then we had to calculate the spacing of the shear reinforcement. We had to calculate this particular spacing, so we did that. And then we had a problem wherein there was a column subject to a axial load, but then we were being asked what is the maximum design moment that you can apply on that particular column. So we had to look up interaction diagrams. Pick up the proper interaction diagram, calculate our Kn and Rn value, find out our rho, which is the percentage of I think what was that 2 1, and then pick up, go there, pick up this value, and this was nothing but Pn times of E divided by Fc prime Ag times of H. We knew this as I think what 165. 165 I think times of this that you calculated your mn, and that is the moment. Multiply with the strength reduction factor, and we calculated the moment there. Okay, and at the very end we did a problem where in the problem there was a column on the slab sitting on a column, but unfortunately it was at an edge. This is a continuous corner. This is a continuous side of the slab, whereas this is a edge. Okay, and we had to figure out where our critical um, plane is, shear plane is, and then calculate the value, uh, calculate the shear strength of that entire thing. Okay, I hope you enjoyed it. If you have any questions, let me know. But then this should give us a decent idea about flexure, shear, etc. Thank you.